Good morning, grade 11s. Thursday, May the 28th. Just got a really short lesson for you today. In fact, just going to quickly get into it. I'm going to give you one example of a convex mirror and how to draw those diagrams, because they're slightly different because the light rays are diverging, not converging like the concave ones you did yesterday. The diagram rules are the same, and again, the diagram is just for your reference. It is the formulas that are unchanged that will find you your answers. All right, but here's how you quickly draw it. I've got a question here. The question says that we have a convex mirror with a focal length of negative 0.5 meters. And remember now that the negative sign is simply telling us that it is behind the mirror, right? The focal point on a convex mirror is behind the mirror. This is our reflective surface on this side, focal point's behind. That means we have a curvature, a radius of curvature, a center point here, that would be 1 meter. Remember that relationship between focal point and radius, right? Focal point equals r divided by 2. All right, so there we go. And then the question says we have a 2 meter high object, so I've labeled HO as 2 meters, sitting 5 meters from the mirror. So HO is 2 and DO is 5. Now, before we get to the formulas, let's draw the picture using our rules for drawing these pictures, the rules for ray diagrams. So, again, the first rule is any ray that is parallel to the principal axis will get reflected in such a way that it goes through the focal point. Now, these rays can't actually go through the focal point because they're going to get diverged, right? But what we want to do, and I'm going to use a rule just so you can see this, what happens is they get reflected, they diverge away in such a way that the reflected, or the reflected ray would go back through the focal point. Okay, so you see that? This ray gets reflected, this is the reflected ray, and if I project it in behind the mirror, it would go through the focal point. All right. The second rule, and we'll only use the first two because the third one we don't necessarily need, but the second rule says that if we have a ray that would be going through the focal point, so here now, this ruler would be going through the focal point. There we go. And I'm going to draw a line here. Okay, if I continued it back, it would. Made a mess of that. The reflected ray would be parallel to the principal axis, okay? And it is again that reflected ray that gets projected in behind the mirror. So draw a dotted line this way. All right, so there we have our ray diagram coming from the tip of that arrow, meaning that the tip of the arrow is going to be at the intersection point there, and there will be my arrow, okay? Something like that. Now let's go ahead and use the formulas to find the information that we want. We need to find DI first, so to do that we're going to use our formula 1 over F equals 1 over DO plus 1 over DI. Put in our numbers. We're going to go 1 over negative 0.5 equals 1 over 5 plus 1 over DI. All right, let's simplify this. We are going to go negative 1 over 0.5. Now, I'm going to simplify this even further right away. 1 over negative 0.5 is 2, right? 1 divided by a half is 2. So I'm going to make this negative 2 minus 1 over 5 equals 1 over DI. Cool, eh? And so when we punch this into our calculator, we're going to go negative 2 minus 1/5. We're going to get negative 11/5. Okay, so we're going to get negative 11/5 equals 1 over DI, which means that DI is going to equal -5/11, or as a decimal, we would have 0.45 meters, -0.45 meters. All right, so there's our DI. And again, the negative sign is just telling us that it's behind the mirror, and we can see that it is behind the mirror. And we can also see that it is inside the focal point. The focal point was 0.5, and our image distance is 0.45. So we can see that our diagram is reasonably close to correct. All right, now we're going to find our height of the image. And so to do that, we're going to use the magnification formula. So again, magnification equals to HI over HO equals to -DI over DO. And so we're going to plug this into, again, we'll forget about the M part, we don't need it. And we're going to multiply the HO to both sides, so that means HI will equal -DI, which was -0.45, times HO, which was our 2 meters, divided by DO, which is, again, 5 meters. And if we do that and punch that into our calculator, we will get 0.18. Yep, that is correct. All right, and so again, we can see, yeah, that makes sense with our diagram. We had a 2 meter tall height for the object. Our image height is definitely smaller, so that works. We get a positive number here telling us that it is upright. Right, it's above the principal axis. We talked about that yesterday. If we got a negative, that meant it was inverted. All right, so again, just using the formulas gives us the answers, but it is the diagram that tells us whether our answers are correct or not. So there you go. You're going to get an assignment today, similar to yesterday's assignment, except they're going to be convex mirrors today. So have fun with it, and we will see you again tomorrow.